So starting from logistic regression, nearest neighbor classifier, decision tree classifier, random forest classifier, we have seen many classifiers. Next, what we are going to see is the support vector machines classification, where so far we have seen distance-based classifications by using nearest neighbor. Then we had purity impurity-based classification by using decision trees. Then we have seen linear classification by using logistic regression, and then we are going to see something different, that is hyperplane-based classification. Let us see how it is going to work, right? So we'll have something like this. So I took this. Let me take my epic pen also, right? Now I have set of apples here and set of lemons here, say, right? Some set of apples and lemons are here. Now we need to have some discrimination between these two fruits and classify them into two different classes. So that is what our aim is going to be there. Now, what is the general role of this SVM classifier is, this is, we call it as support vector machines. And there is a meaning of saying why it is support vectors, right? We say it as support vector machines. Let me write that. Right, there's a thing. So now what the SVM will do is, it will first scan the data points one by one. It will be doing some scans over here, and it will check that when I scan over here, yes, only apples are there. Then I say here scan, apples are there. Here I say apples are there, and so on. It will scan one by one, and at some point of time, what will happen is, it will find something called a different fruit, say lemon, right? A different fruit, say lemon, is actually there. Now, what will actually happen is, when I scan over here, I'll be having some 100% confidence saying that yes, all the fruits are going to be apple. So the confidence of saying that the fruit is going to be apple, say A, is actually 100% up to this point. But when I actually scan here and found a different fruit, say lemon, my confidence level of A is going to be decreased. My confidence levels of A is going to decrease, and the confidence level of lemon is going to increase at this particular point, right? So every data point in a particular data distribution, we call it as a vector, but there is something called as a support vector, which I mean this particular point. This particular point, I say it as a support vector. Why? Because this point is actually giving me some discrimination on what is the next class that is going to start, right? So far I'm actually confident at the maximum level that all the fruits over here are apple. But when I cross over this particular point, I get some different view. So I need to understand that after this, there may be a point for lemon, right? Then I go and continue my classification. Here I scan, here I scan, here, and so on. And over here I find a different fruit, right? But the color may be same. It may be a different fruit, but the color may be same. Then now what happens? There will be again a change in the confidence level of apple and lemon, right? There will be again a change will be there in the confidence of apple and lemon again in this particular point. So I also call this particular portion as a support vector. Next, I proceed my thing over here. If you say here, everything is going to be a common fruit, and at this point of time, what will happen? The confidence of lemon will be at 100%. So whatever data point comes over here, I'll be saying with 100% confidence that they are lemons. So this is actually the typical procedure that will be used by the SVM model to recognize the data point, whether it will be in a class 1 or class 2 and so on. So say to be a binary classifier consists of two different classes, say apple and lemon. If I want to do a separation between these two classes, then what I have to do is, I need to find something like an optimal hyperplane that separates these two classes. If I allow a line like this and say this class is different and this class is different, then what will happen? This particular data point may be classified as wrong, and this particular data point may be classified as wrong. Others may be classified as correct. I cannot draw a line like this. I cannot draw a line like this. Like this, I cannot draw a line. Like you can draw only an hyperplane. That hyperplane should be like this, and my role is to find an optimal hyperplane. So ultimately, what we actually require is we require something like an optimal hyperplane. If I was able to find this optimal hyperplane, then I'll be getting a topmost accuracy compared to other sorting algorithm, other classification algorithms. So I need to find this optimal hyperplane. Now I generally ask you a question. The given data, what is shown here is linearly separable or not. Whether this data is linearly separable or not. See, I'm asking you a question. I want everyone to get unmuted and say whether the given data distribution, see apples are here and 11s are over here, whether these are linearly separable or not. Whether my question is clear?
Yes, sir.
Yes. So now what I ask is whether these points are linearly separable or not. Whatever comes to your mind, you say whether there can I draw a straight line like this?
Separate.
This is class 1, this is class 2. Can I say like that or not?
Sir Esker, we can draw the straight line by consider this marginal distance. Sorry,
Yes,
margin.
I can
Hyperplane.
actually consider many straight lines, and those straight lines in future I'll be calling them as hyperplanes. I'll be giving why I call it as hyperplane. I can draw a line like this. I can draw a line like this. I can draw a line. Sorry, I can draw a line like this. Anywhere I can actually draw a line. So to say that they are actually in a different classes, many different lines are actually possible. So this is what we come and say that we need to find something an optimal hyperplane for a linear space. So we can say that this blue line may be the optimal hyperplane separating these two classes. But whether there will be only one line to do that, no. There may be n number of lines that can actually do that. You can have several lines doing this, but which line is actually more efficient? We have to calculate, right? But everything is going to be an hyperplane. This is an hyperplane. This is an hyperplane. Everything is going to be an hyperplane. But which is an optimal hyperplane? We have to find. Now there comes a question: what is the optimal hyperplane mean? So optimal hyperplane means that the classification accuracy is high, or there should be a distance between the support vector to the optimal hyperplane, right? So I say already said you a glimpse on what is the support vector here. A support vector is a portion that helps us to discriminate two different classes. So I can call these two as a support vector as per now, and it is my own wish, and I have some special parameters to consider the number of support vectors, right? So I should draw a line in such a way that these 2 points are as far as to me, right? So I have some metrics to do that, and visualize that also. So so you think that many hyperplanes are actually possible, and an optimal hyperplane need to be selected. Now comes how to select those optimal hyperplanes. See, let us see here. Now a blue line is drawn. Now what I have did is I have chosen some support vectors here. Here is one line which is actually covering my support vector in class 1, and this is a line which is covering support vector in class 2. So now I call this particular distance, say, d negative, that is distance towards the negative class, I mean. And if I call this is going to be d positive, that is distance towards my positive class, say apple. So the sum of these two distances, say d positive of to the class 1 and d negative to the class 2, the sum of these two I call something called as margin,
Marginal.
right? So like you can just say it, we are going to calculate something like a marginal distance between the chosen support vectors. I am choosing this as one my support vector, and this is my one support vector. There should be much distance between these two support vectors. Like that, I need to choose my support vectors. I cannot choose these points as my support vectors alone. Surely these should be there. Why? Because they are actually closer, right? So I'll put a line over here. I'll put another line over here. Now, if I put these two lines, now I'll be in a better position to identify the mid portion where this have to be. The mid portion where my hyperplane would have to be. Then I can call this as an optimal hyperplane. So I call this as an opt hyperplane or optimal hyperplane. So this optimal hyperplane will be working efficiently in separating these two classes. How in the sense, if it is actually located, like, see, if I'll take another example here. Say, for example, this is another example where this is also a good hyperplane, but we need to understand whether it is optimal or not. Say, for example, in the previous example, if I get something over here, let me go into the previous example once and draw something there and come back to here. So, in the previous example, say I draw a line over this particular portion, I draw an apple. I'll take some other color. Say I am going to draw an apple. Say, for example, I draw something an apple. Why the pen thickness is increased?
Big gap.
Oh, point is increased. Yes, I say I draw an apple over here. If I draw an apple over here, what will happen? This hyperplane will classify this as apple itself. It will not classify as lemon. Why? Because there is an equal strength given to both the classes, and I draw it exactly in the middle. But if I take a contrary over here, and if I didn't get an optimal hyperplane, say for example, I take this. If I take this, then what will happen? This is actually even more closer. And if I take something over here as a lemon or something over here, this optimal hyperplane will give me more precedence for the lemon rather than the apple, because there is more space for the lemon class rather than the space for the apple class. The space for apple class is very less, whereas the space for lemon class is very high. Because the plane is actually not optimal, it is one-sided. It is actually giving, it will classify the test set mostly as lemon rather than being as apples. So there should be much distance between the two support vectors. Here the number of support vectors chosen is 2. And how you will be choosing? I should choose based on the margin value. So the first hyperparameter what we are going to consider here is the margin. So the margin should be as low as possible, as high as possible between the two data points. For the first thing what we are going to consider is margin. I will be drawing the margin. I'll be taking any two support vectors. Say this is one support vector and this is one support vector. I should take these two margins and draw my hyperplane exactly in the mid in such a way that on both the margin ends I can have some equal width. So this together I call as something called as margin. So if the margin is very less, then it means that it is not going to provide proper result. It is biased. It is biased towards one class, and the other class will not get any result during testing. So the first one is margin. And I'm making the margin point very clear. I want
Sir,
chorus answer from everyone, not only from Yogender.
Yes, sir.
Yes. So the thing about support vector machines, what you have to remember when you go for practical as well as some thesis, support vector machines will not use directly the lines. It will use something called as an optimal hyperplane. How you have to use the hyperplane? The first thing is you select any two support vectors that is closest to points from two different classes. For this class, the closest point is going to be this particular data point, and for this class, the closest point is going to be this particular class. You have to fit the closest point like this and call it as support vectors and compute what will be the optimal hyperplane. Right? This is what we have seen now. Now let us proceed to the next factors what we can actually influence. Right? So this is actually my best hyperplane here. Now, if the data is not linearly separable, right? We can easily identify that this is not linearly separable. Why? Because I cannot draw a straight line here or here to separate these two classes. Surely two classes are there. I cannot separate like this, right? So what should be happen? I should introduce something like to make this
support
separable,
classes.
right? So I need to introduce something to transform this to some higher dimension. If I want to transform this to higher dimension, what I can actually do, instead of having x1 and x2, I can have another axis, say x3.
Z or
I can have another axis, say x3. So this will become a three-dimensional view. So if it becomes a three-dimensional view, then what will happen? I can actually draw, instead of putting a line here, I can put a cardboard and assume I can put a cardboard. So this cardboard will be between this lower, say all the apples are in ground floor and these lemons will be in the first floor. In between, I can put one cardboard. So that is actually the hyperplane separation. This factor of converting from lower dimension to higher dimension is actually called as,
kernel, support kernel.
yes, converting or converting from, sorry, my handwriting going in less than, converting from lower dimension, say 2D, to higher dimension, to any higher dimension what you want. You can actually use something called kernel. So we have various kernel function. For using this, we can use something called as kernel. So these kernel, we actually call this as a kernel trick. How we are using the kernel trick is these points are not linearly separable, but even though they are not linearly separable, I can increase their dimension to make them visualize that they can be separable. Right? If I increase this dimension, these lemons will go up, or these apples will go down, or so on. Because everyone will not be in the straight plane. Surely they will be on a separate plane. I can draw a cardboard over there, and then I can, instead of drawing a linear hyperplane, I can actually put a quadratic hyperplane so that it actually separates both lemon and apple. Many kernel functions are there. So everything for we are going to see practically 5 different kernel functions and visualize how each kernel function is giving us different levels of accuracy. That we will be seeing in Colab, right? So the second tuning parameter, what you need to keep in mind with respect to SPM is the kernel function, right? So the previous thing, what is actually available here is can be converted to something like this. If I increase the dimension, if I increase the dimension, you have another axis here. See, this axis may be called as x3, and this x3 axis is actually making this lemon to go down, maybe in the ground floor, and apple be in the first floor. Now I do some hyperplane over here. This hyperplane serves as a separator for both class 1 and class 2. So why which this is possible by using something called as kernel function, right? So far we have seen 2 hyperparameters for the support vector machine. Say one is actually margin, which is used to identify the optimal hyperplane between the two set of classes.
So
Second
linearly
comes,
separable.
yes, two separable classes, two linearly separable classes. Second comes something called as kernel. Even though my model is not linearly separable, if it is non-linear, then I can convert their dimension to somewhat higher dimension so that they can be separable. There are various types of kernels available. Everything we are going to see practically and how each of them is going to affect. With this kernel itself, we have many things to consider. Why? Because this kernel will increase complexity of the model. Why?
Dimension. It increases the dimensionality in number of
Yes,
dimensions.
yes, because the number dimensionality will increase, and we literally know that if the dimension of the particular data increases, then the complexity also increases because everything is going to be a polynomial, right? We have polynomial kernel, radial
R,
basis kernel, any kernel
RGF,
are there, say,
Egmoid
right?
kernel.
Yes. Now we have another set of data points. Say here we have apple, lemon, everything in a straight line. So this is actually in a 2D. Now if I want to convert this 2D into a 3D, what I can actually do is I can increase the dimension, right? So I can just increase the dimension so that it becomes a parabola. So instead of having the straight line, I can increase the dimension so that it becomes a parabola now, and I can draw on hyperplane over here, right? So if I was able to, if I possible, I'll make you visualize here. Let me take that ppt also, right? So this actually is means the overfitting criterion. Let me go to the previous slides. Yes, here is the margin C. I have a set of data points over here that is actually being selected as support vectors. Now, how many support vectors are selected here? 1, 2, 3, and over here I selected 1, 2. So totally 5 support vectors are there. So my margin is actually like this. So equally divided margin to both positive and negative classes. So these are my support vectors. So how many support vectors I have selected is 5 support vectors. And even the number of support vectors you select is also an hyperparameter. So that is also in our control only. When we train the model, the support vectors also we can select. And this is actually the regularization parameter. We'll see that separately. I'll say the kernel first. So what is that kernel is transforming the data. I don't see that kind of image is not available here. Only I have this. So if it will increase towards some higher dimension, that will actually make us the data separable, right? So far we have seen what is that margin as well as the kernel. Now we will see this particular term called as regularization parameter. We have already seen regularization in linear regression itself by seeing two different type of regression in L1 and L2 normalization. We have L1 and L2 normalization, say lasso and ridge normalization. Everything comes under regularization that is literally used to reduce overfitting, right? So this regularization parameter denoted as C in Python, we will be having that. So this what it will actually do is it will actually understand whether the model is going to be overfitted or underfitted. Let us see this particular example. We have the data here. Now a hyperplane is drawn over here, and if you see here, only one point is slightly touch in the positive end, that is 0, and in the x points, I have only a small touch over here, and other things are very good, right? That is actually I'm trying to fit the model as good as possible. If you see here, I'm not taking any much risk. I'm actually putting some optimal plane over here, and I was not caring about these in error. This 0 is being classified as plus, and this 0 is over here, right? I'm not caring much about this particular error alone. If I care about this error, then it will become an overfit to the training model. So if you increase the C value, then your model will overfit. Else your model will be in under, and if you're not caring about the C value and leave it as low as possible, then the model will become underfitting. So an optimal C value is required. So that's what regularization parameter. And this can also be recognized like this. If it is in a lower dimension, then it means that you are actually going along the pathway of the entire data distribution. To make the classes exactly separable, we are actually bending the lines like this to make it as overfitted as possible. Usually we don't encourage for this kind of overfitting in your training data. Why? Because if the training data is much overfitted, then surely my testing accuracy will not be higher. So we usually do not encourage overfitting, and this regularization parameter C should be some optimal value ranging to a particular depth when we consider our particular data. So if the data is actually more similar, many independent points are actually being dependent, then we must be very careful on how to set this particular C value, right? So keep in mind, so far we are actually doing this margin, kernel, and C value. So why I'm asking you to keep this in mind is when we go into the practical collab, we'll be setting the values for each of these points and we'll be executing. So at that time you can understand what is the role of each of those points. So margin, it is actually the hyperparameter where the model itself will recognize and where to place my optimal hyperplane. Whereas kernel, as Yugandhar said, it is going to be a thing which is going to transform my data from a lower dimension to a higher dimension. Right? Now, people may ask that whether SVM surely have to use kernel. No, it is not required that SVM surely have to use. If the data by default is separable, then we don't want to use kernel. Else, we have to use some kernel trick and we use the external function and we classify the data. But we should think clearly that introduction of the kernel will increase the complexity also. If you are able to bear that complexity for doing that particular classification, then you can go with that kernel SVM, right? Next comes the regularization parameter C, which actually understand whether the model is going to be overfitted or underfitted. If the C value is very large, then we say that the model is going to overfit, and if the C value is very low, then we clearly say that the model is not doing anything, it is underfitting. So we need to find an optimal value for C also, right? The final hyperparameter what we have to discuss here is the gamma. Yes. So the gamma is nothing but I said right, even the number of support vectors, what you are going to consider is also an hyperparameter, right? So now see, this is the gamma value. I set the gamma value to be higher. Now this is my hyperplane, and see how many points are actually being recognized for support vectors. 1, 2, 3, 4, 5, 6. 6 points are recognized as support vectors. The 6 points that are more closer to this particular hyperplane. If needed, I need not take these also. I can also consider this as one hyperplane and these three as another hyperplane. I can continue with four support vectors itself. I can also finish with four support vectors. These are actually extra. If needed, we can add these also, right? And coming to here, see, I have taken many points as support vectors. So if you consider more points as support vectors, this low gamma value will also have an effect in overfitting. Why? Because it is not possible that every point in class 1 will be of sufficient distance from every other point in the class 2. It is not at all possible. Only the points which are actually closer to the margin in both the ends need to be at a particular distance. It is not that every point in class 1 and every point in class 2 should be at a much larger distance. Then it is very difficult to fit that particular criterion. So we do not prefer low gamma value, right? We actually prefer as considerable gamma value. Why? Because if I increase the number of support count also, the model can overfit as well as the complexity of the model also increases. Say for example, if you are actually using kernel as well as low gamma value, then what will actually happen? My kernel will be in 3D or 4D, and if I if I decrease the gamma value like anything, then what will happen? Then every data point from different axis need to be compared to other data point in a different axis. So every comparison accounts to a computation cost, and the overall complexity of the model also increases. It is not only about the accuracy, because if the training accuracy is higher, no one is going to bother. I was bothered only about the test accuracy or the score accuracy. So overfitting can also be possible when you use a low gamma value, right? So in a support vector machines, this is actually the summary. We totally have something called as four hyperparameters. Say margin. Next is this gamma, regularization parameter, and finally kernel. Right? Now, can anyone say about what is margin? Except again that what is margin? If I draw an axis like this, or you just answer me yes or no like that. If I draw an axis like this, we have two separate points. Say I have circles over here, and this is my hyperplane. What is margin here? So I'll draw something. I'll first select the support vector. So these are the, assume that this is one support vector for me, and this is going to be another support vector for me. Then what will be the margin? I'll be considering this point as one margin, and this point as another margin. And what is this distance? Say this is the distance for positive class, and this is the distance for the negative class. The sum of these two is actually the margin, and my hyperplane should be exactly in between these two plane things. That is actually I consider as margin. Now how many support vectors I have here? 1, 2, 3. I can say that I can have 3 support vectors. Now I'm making it clear. Now going into here again. Now we have this, right? Now that is about margin. Let us come on to the next thing. If this is a margin, then what will be the regularization parameter here? What is the regularization parameter here? Or I'll draw that and show. You say me how the regularization can be here. If I have set of points over here. Now what will be the regularization here? High regularization value should be, regulation value is considered as C, whether C should be higher or lower. If C is high, what will happen? If C is low, what will happen? If C is high, what will happen?
Overfitting.
It will be considering as overfitting. Why?
టెస్టింగ్ అక్యురసీ ఎక్కువ ఉంటుంది కాబట్టి.
Yes, you'll be having the testing accuracy, but if you want to say with respect to this particular point, I can also show you this particular image which we have seen here. See, my hyperplane will be very close, very stringent. But here, if I want to draw that hyperplane like that, I can draw it very stringently like this. Say for example, I have a data point over here. Then what I will do is I'll draw a particular hyperplane like this with so many all the margins, everything exactly going in middle of this. I don't care about how the points are actually moving. I'll go as middle as possible as possible here without caring about the margins. If I care about these 2 points, then my margin will be very low. So because the distance between this and this, if I take, the margin is very low. Usually what SVM says, the margin should be as high as possible. But for this particular optimal hyperplane which I have chosen, the margin is very low. So I should not consider these 2 points as support vectors. Instead, I can consider these 2 points as support vectors. I can increase my hyperplane. I can divert my hyperplane to some other axis to make the particular thing happen. Right. So this is actually with respect to the regularization parameter. I am making it clear.
Yes, sir.
Yes, sir.
Yes. Right. So third comes the kernel function. When we will be using kernel function, can you say in only one word when you like I will use kernel function?
Increase the dimensionality.
One word. Data is dash.
Non-linearly
Yes,
separable.
that's it. If the data is non-linear, then immediately I'll use something called as kernel. Right. So by using kernel, I can increase the dimensionality and I can make it linear. Coming to the final point, gamma. So this is very simple. Instead of considering 3 or 5 points as support vectors, I can consider as many points as support vectors. Now the question is, if I increase the number of support vectors, it is good or bad? If I increase the number of support vectors like this, then what will happen? My gamma value will actually reduce, and this will increase the complexity of the material, as well as overfitting also will happen. Right? Am I right or wrong? If I increase the number of support vectors, and every point need to be compared. That is actually not possible theoretically. If there is a distance calculated to the closest point, then that itself is enough. There is no need of calculating why these distances are actually present, because these front runners are actually the people who are going to say how far the data is, and these people can say how far the data is. Others, if I take also, there is no need of taking these people, because they itself will say how far the hyperplane is going to be getting as classifications, right? So this is actually an optimal way where I take only the support vectors closest to my hyperplane. These things are actually not taken, because if this is taken, automatically these are actually considered, right? So whether number of support vectors should be high or low.
Low.
Yes, number of support vectors should be at a particular level. So if I increase that, then it is actually not needed. It will increase the complexity of the model. So gamma value should be high, right? Yes, so these are the 4 parameters. In the next class, what we'll be doing is, once we complete a random forest, we'll be seeing for SPM also on how each different kernel is going to work, right?